this data out of this device as quickly as possible. Remember, we are running in a PC that has other applications running also at the same time. We should free up time for those applications. We should not use the entire CPU for ourselves. So this is just a dual-core old machine, and we are kind of very low profile with all the drivers and the runtime running here. Okay, cool. And it supports virtual sensors, test tools, and later I will describe this thing of kinetic. And then there is the toolkit. The goal of our toolkit is, we know that developers work by example. They prefer to get some working source code, get it into their machine, compile, and start to make changes, then to read the entire Bible about the APIs that we make available. So we provide examples in C#, C++, and Visual Basic, and we provide links to our SDKs, and that is what the toolkit team does. And we are having a lot of success convincing companies to do applications for the Kinect. But now let's dive a little bit into skeletal tracking, how we do this. Any questions before that? Okay? Okay. So the first thing that we do is, we need to calculate that. How to calculate that? So the goal is, we have this projector here, and we have a camera that is a little away from the projector. I will show later exactly what the camera is seeing, but you can imagine that there must be a mathematical way to calculate the depth based on this. Okay? I will show the mathematical way. At the high level, what we want is, we want to give you just 20 joints. So where is the head, where is the right knee, where is the left knee, so that you can make code that is just based on the joints. Oh, the hand moved from bottom to top and so on. You don't want to make software based on, oh, the pixel changed from here to there. That's what computer vision has to offer for you. So the way it is exposed to the developer is something like this. And even though you don't understand the entire source code and even the language here, which is C#, basically you start a kinetic, you enable the device, you say, I want the skeleton data, and when the skeleton data is ready, call this method here, and please, kinetic, start. So it is very simple, and when kinetic has data, it sends to you, and you can just copy this data to your buffer and so on. That's all that is needed in terms of code. So literally 10 lines of code, and you get the data. But let's not focus on this here. Let's focus on what we really do. So the first thing that we need to do is get depth. Any camera can give you the RGB data. The depth is where the secret really is nowadays, and you saw a lot of presentations already with applications of that. So how do you do this? So the thing that the device is doing is, there is a laser pointed at you, but luckily it is a laser that is spread through. So let's go again to our application here and use that application that we have been using to explore the Kinect. So this application here will show you this, and I will ask it in the color stream to show you the infrared. So you are too far away, so I'll have to point at you here. I believe, okay, here it is. So because the pattern is kind of spreading. So basically what is happening here is, a pattern is being sent in infrared. It is infrared because people like to watch, for example, TV or play games with the lights down. So infrared will still be visible there. So what is happening is a signal is being sent here, and oh, let's bring that bit. That's probably okay. So the signal is being sent, and I can calculate that because basically when I come here, the pattern. If I know the pattern of points that is being sent, I know that as I move something in this area, what is happening? These points will be in different distance when seen by the camera. So, some geometry and some math, and I believe that most of you can resolve this problem. So it's left as an exercise, okay? So, basically, this is how it is done, okay? The infrared is spreading a pattern. This pattern is totally diffused, and basically, based on this pattern, we calculate that. So, let's go back and continue getting the information. So after we got that, we can easily do a depth map. So if I have a point in space and I know its color and I know its depth, it is possible that I can even show to you where this point is in space. So I will connect this application here to that other application, and I will show to you what is that the application is seeing in terms of color. Oh, sorry, I have to return color to the RGB string. So let me return color here to show the RGB data. Okay, cool. So then let's go back to that application. Okay, so that is the color, that is the depth as visualized, but here is the cool part. That is me and the depth projection. Okay, so basically, except for you, that I am projecting my points in 3D space. So this information is made available back to the application. And you can see some lines, for example, the device, when it is in the Xbox mode, which is the default mode, it cuts depth when I come closer to 80 centimeters. Okay? And when I can put it in what we call mirror mode, and it will give you the depth even when I'm 40 centimeters away. So, did you all get the idea of that view? Basically, I can then have this depth map being used as the basis for my segmentation, isn't it? The next thing that I need to do is background removal. I need to remove what is the player and what is the background. Okay? So, if you pay attention to the application when I am using it, you can see in that back window there that it is doing a segmentation all the time and creating large blocks of regions. Can someone help me here? Because it can do for 2 people at the same time. So see, it does the segmentation all the time. And if you saw the presentation this morning, segmentation is one of the hard parts, isn't it? But I have that information. So I can segment with a lot of confidence. So that's cool, isn't it? The segmentation problem that is typically the hardest problem becomes far simpler. And how can we do it? Well, you are experts in image processing, so you all know that we can do connected components. So we just really go through the depth data and connect the components that are at similar depth. Okay? Cool. So I have now what? I have this large box that I believe they are something. I still don't know what it is. This is called segmentation map. You can have, even for players that we don't provide you the skeleton, we can give you the segmentation map. Okay? I'm not going to details here because I'm taking a lot of time already. So Okay, now we have a problem. You remember the presentation this morning? What is this problem? What is the problem? What? Parts, fantastic. And that was not kind of rehearsed. He was not here for the rehearsal. So, yeah, people miss the rehearsal. It's fantastic. So, we need to map these two body parts. And that is the technology that you really need to learn if you want to have any future in computer science, which is machine learning. Basically, we have one of the best machine learning algorithms in the world right now. Because we sold 20 million of these devices, we know people are extremely happy. But what is the thing that you need to do any machine learning algorithm? What? Training data. You didn't come to the rehearsal. It's very good. The key thing it is, you need this thing that we call ground truth. Data that is annotated, that allows you to create the basis for your machine learning. And that is the big difference between industry and academic world. In the academic world, you can kind of come here and say, I tested my algorithm with 12 people, isn't it? I captured 12 people, I have 100 frames, and I tested. Okay? How many people do you think we test these things with? Tens of thousands. How many frames you think we have for ground truth? Millions. Millions of frames where someone is paid at $20 per hour to go and annotate. The hand is here, the arm is here, it's here. Millions of frames. We have people that train the taggers. These people are called the taggers. We have the taggers, we have the people that do quality control over the taggers, we have all those things. And then millions and millions of data points. Because whoever has any background in machine learning will tell you, the algorithm doesn't matter. What matters is the data. If you have the data, it will solve the algorithm problem. But if you don't have the data, it is a guess. So we have then to map this thing that is in front of the computer to a graph. A graph that is the graph of the structure of the body. This morning, for example, you heard about this thing of the difficulty of mapping the graph that comes from the input to the graph that is your known structure. We know that typically the hand is next to the arm, that is next to the body, that has a head, and some things like this, isn't it? So we have the graph that we are seeking for. Now we need to map the input to this. And that is where machine learning helps. We have this thing that it is these pixels in the 3D space, this point cloud, you probably heard of this. And we have a classification problem. Which body part, if that is a person, which body part this pixel belongs to? A lot of people try to solve this problem doing the segmentation of the body and then trying to simplify the graph matching. We tried something different. Indeed, the idea is from James Shotton, who is one of the co-authors of this paper, was published last year, kind of outlining the algorithm. What if we don't do the segmentation? What if we try for every single pixel to explore the features and try to use the structure that the body will have as part of this energy minimization equation that we are trying to solve? And that is where the algorithm, how the algorithm works. So let me show you a pre-recorded video because this is part of the paper, and I want to really showcase what they did as part of the paper. And it is not showing here. Let me see why. And if needed, we will have to go to the backup solution. This is a problem that typically happens because of the schematic with 2 monitors. So let me close this and close this that you have seen already, so that we can focus on the video. Okay, so okay, so this is how the thing works. So the problem that we have is to do that classification. And for the Xbox, this had to be done in less than 5 milliseconds. So in the Xbox, of course, the algorithm was optimized for the Xbox. So this is the depth info. So it is very hard to do segmentation, isn't it? Infrared doesn't segment very well. So what is done, it is a classification, a very noisy classification map that indeed tries to classify every single pixel. Then you calculate the centroid for that mass that is classified according to the proper region. And then you have there the several views, and one is from the top of the body parts. Okay, so this is how the problem is solved. Basically, running this very efficient code that is classifying everything all the time. It will misclassify a few pixels. And because this is based on machine learning, it will sometimes not work. Because see, if you get into positions that people don't get at those positions normally, it will not work. Machine learning is perfect for classifying something that is within the input data, but when you are outside, it's not very good. So, back here. Okay? So, any questions so far? You still don't have the skeleton data. Why? Why you don't have the skeleton data? Even though you classified everything, even though you can have easily the center of gravity for a region, why is that I cannot give you this as skeleton data? See, you don't make questions, I make them. Nobody?
Spatial relation between them.
There is a special relation. So basically that is exactly the thing. It is, you still have problems because machine learning will classify anything. Okay? If you put a dog in front of the sensor, it will probably classify the regions as something. But those don't match a human. A human has certain kind of limitations. Humans don't kind of, except for a few humans from humans don't do poses like this and things like that, and the leg is here and things like this. So you still need to filter out a certain kind of set of skeletons that they will come from the classifiers, but they don't look like good skeletons. Like sometimes the bones are kind of bent. It's like, wow, for the person to do that position, the bones have to kind of bend in a way that it is impossible. You know it is impossible. But the machine learning classified the parts, it found the center. The other thing is, the entire game industry is optimized for you to face your TV, isn't it? But then you have games like golf, and the thing doesn't play well. If you see the golf game for kinetic, you have to play like this, looking at the TV. So the reality is, you still may have skeletons that are not really skeletons. So we have a lot of code to filter out those skeletons that, yeah, they don't look like skeletons. And then we finally return to you this output. And that is done. That is the past. What is that we are doing for the future? Before we go into questions and finish, kind of on time. There is a huge problem with the legs. Most people, they put the sensor in certain places, and then the legs are invisible. So you saw that even when I was doing the demo here, most of the time my legs were not visible. So the sensor, when it starts on the Xbox, I don't know how many people here have the Xbox and the Kinetic. When it starts, it goes through all angles, trying to find the best angle in which it can see the entire person. Of course, if you want to do this in the Windows software, you have to do it by yourself. But this problem is called crab legs. The legs keep dancing because the classifier keeps kind of changing its mind regarding where the foot is for each foot. So sometimes you even see this in Xbox games. There are Xbox games when sometimes you see, for example, tennis is common. You see the legs kind of dancing. And this problem is known as crab legs. We know about this problem. It's just that to solve it, you have to have a sensor. This sensor has a huge problem also. It was done for houses in the United States, where they have these huge houses. My house in the United States, I believe my apartment that I have in Belo Horizonte fits in the living room. So the thing is, it's done for the houses in the United States. In Europe, houses are smaller, even in Brazil. So the sensor is optimized for you to be 2 meters away from the sensor, playing these large TVs that Americans have. So yeah, it's not very good for Japan and other countries. So the sensor was not really thinking about this kind of angle, the angle for the vertical, and that introduces this problem. The other problem is smoothing. We are aware of this. We have some parameters that will smooth out the data for you, because the data can be a little jumpy if you just look at the raw data coming from the skeleton detector. Anything not in the training. Indeed, it is an interview question that I make to people that want to apply for our teams. And I ask, what do you think that happens if people misplace the sensor like this? What? Nothing. It doesn't work. Why would it just not work? What is that just not working with you? What? The depth would be okay. The depth would be okay, exactly. So why it is just not working? Skeletal tracking would not work. So, I need to create a head here. Let me try to create a head. So sometimes I think just like things that reflex. So sometimes I manage to make it see a skeleton. Anyway, So the thing it is, why? Because it tried to match, it found a match that, see, the joints are not so confident, and they are jumpy, isn't it? But they found it. Again, this is computer vision, state of the art. There's nothing better. If you have something better, you sell a lot. So, and it keeps seeing, see? It's, oh, but I believe there is a person. So, really, it's seeing him, but see, his legs are not visible. So, it is just kind of jumpy. So, and that is a problem. The next big problem is this thing that we call mini-me's. Sometimes there are small regions, and it is very funny because sometimes the computer sees those things, and then you go there and you kind of, oh, yeah, from the distance I could see a person there. It sees the persons that obviously are not there, but then you squint a little bit your eyes and, oh, yeah, if it filtered out that mini-me, also probably a child there would not have been seen. It's very hard to solve this problem. Multiple devices, it is the top request for us right now. People want to connect 2 or 3 devices to the PC so that they can make games with 4 people, they can cover a larger area. And our skeletal tracking, because that was the way it came from the Xbox, can only work for 1 sensor. And the top reason is performance. I told you, it takes, of course, indeed, brand new machines. We have a machine in our lab where we connected 8 devices, run skeletal tracking for 80 devices, and it's fine. But not everybody has this machine. Many people don't have machines worth $25,000. Okay? So we have those machines for our testing, but we need to make it work for the typical machine. So we keep optimizing performance. Maybe if it is the only solution, we will go back to requiring a GPU, which by the way is a complaint from people. People that have GPUs complain, why don't you make these things on the GPU? I have this machine with the top graphics card that I decided to buy. It's not using. This graphics card is sitting there doing nothing. So, I hope what I have shown you basically is consistent with my conclusions at the beginning. So, it takes a lot to do software. You see, it's data typing, learning, machine learning, training a lot of data. We code very little. Very little new code is done for the project nowadays. What we really succeed is because we have a lot of people that know a lot of areas that are enabling the kinetic device to work on those areas, and developing software is far easier than developing software is far easier than developing software. Thanks. Thank you.